Tonight, we begin our slow exploration, not of grand voyages or dramatic discoveries, but of a much quieter, more fundamental process. We are moving toward the map, but first, we must examine what came before it, the basic, almost subconscious need to simply know where we are and where we are going. Please, allow your thoughts to slow and settle as we consider the primal impulse, the comfort of spatial recognition. Before there were lines of latitude and longitude, before there were symbols for forests and mountains, there was only the space itself. For the early human, this space was not an abstract concept. It was immediate and profoundly relevant. It was the space between the shelter and the source of water, the space between the hunter and the herd. Every step taken was an exercise in pure, practical geometry. But this geometry was not recorded on parchment. It was recorded in the quiet cellular memory of the body. Imagine the feeling of emerging from a cave entrance or stepping out from a dense copse of trees. The first action is almost certainly an act of orientation, a soft scan of the horizon. Is the sun high or low? Is the wind coming from the coast or the valley? Which large, distinct boulder or unusually shaped tree is still visible from this new vantage point? This subtle, moment-to-moment recognition of landmarks provided the first deeply reassuring sense of order. The landmark was a fixed point, a certainty. Its presence was a quiet affirmation, you are here, and this point remains unchanged. We seek this comfort still, the fixed point, the known object. Even in the darkness of a quiet room, the presence of a familiar shape, the line of a window frame, offers a gentle confirmation of scale and place. Directional systems, the slow sweep of the sun. The simplest, most ancient system of direction was also the most reliable, the celestial mechanics of the sun. The motion of the sun is a continuous, predictable, and entirely unexciting sweep. It rises in one general region, it reaches its peak altitude, and it descends in the opposite general region. This motion provided the first great reliable clock and the first great reliable compass. To walk toward the rising sun was simply defined. To walk with the afternoon shadow extending behind you was an equally simple and clear directional instruction. There was no need for degrees or magnetic north, only the smooth, slow progression of light and shadow. Consider the complexity of establishing a truly fixed direction using the sun alone. It changes its path slightly with the seasons. A line drawn based on the summer sunrise would be slightly inaccurate come the winter solstice. This introduced a necessary level of mild, predictable variance which the early mind had to silently catalog and accept. The knowledge was internal. It was subtle. It was learned not by reading a manual, but by quietly watching the sky for years, a patient, necessary study. The role of the stars and the celestial zenith. When the sun set, the directional task became marginally more complex, but still offered reliable, distant points of reference. The stars, of course, presented a ceiling of quiet, fixed lights. Most constellations drift across the night sky, just as the sun does in the day. But for those in the northern hemisphere, there was the profound, silent comfort of the pole star. The pole star, or Polaris, maintains an almost perfectly stationary position in the sky. It is the spindle around which the great cosmic wheel appears to turn. It is not dramatic, it is merely dependable. To find the pole star was to locate north, and once north was known, the rest of the cardinal directions, east, south, and west, simply fell into their appropriate, unhurried places. It was a simple, four-part spatial system available merely by looking up and confirming the stillness of that one particular point of light. Think of the stillness, the cold, geometric certainty of a star that simply does not move. A comforting anchor in the vast, rotating darkness. The transition from oral tradition, soft knowledge. For generation after generation, this vital spatial knowledge was passed down through spoken word. This is what we call the oral tradition of navigation. A journey was not described in measurements, but in a sequence of sensory details and actions. You will walk toward the setting sun until you pass the twin-scarred river oaks. Then you will turn slightly left and follow the scent of the wild sage for the duration of the midday shadow. After the sun dips low, look for the deep valley shaped like a resting animal. The water is there. The knowledge was soft. It relied heavily on memory, observation, and sensory input. There was flexibility. If the river oaks had fallen in a storm, the traveler still had the scent of the sage and the familiar shape of the distant valley as backup. This soft, fluid knowledge was efficient, but difficult to share beyond a small, known group. It lived inside the speaker and vanished when the speaker was silent. This reliance on memory and the constant soft pressure to retain complex spatial details eventually led to the quiet need for permanence, a way to externalize the map, to secure the details against the failure of human memory and the inevitable passage of time. This is where the transition begins, the slow, quiet move from the story in the mind to the line on the clay. The first externalization, simple drawing on the ground. Before maps were drawn on durable materials, they were transient, temporary diagrams, drawn with a stick on damp earth or scraped onto smooth sand, a small, momentary record. These diagrams were intensely localized. They were not global representations. They served only to solve a very immediate problem. How do we get from here to there? A finger would trace a simple winding line representing a river. A small stone would be placed to represent a hill, and a cluster of pebbles might represent a small settlement. The entire map could be erased by a single sweep of the wind or a light rain shower. What is fascinating about this stage is the omission of detail. The creator of the sand map only drew what was necessary for the conversation. They omitted the irrelevant. The distance was rarely proportional. The angle of a turn was rarely precise. It was a conceptual sketch. a fleeting idea given temporary physical form. The power of the map lay not in its accuracy, but in its agreement. The two people looking at it agreed for a brief moment on the spatial relationship being discussed. This simple act, the gentle scraping of a line in the dirt, is the foundational act of cartography, the first attempt to freeze a moment of spatial understanding and hold it still. The necessity of scale and symbol. As communities grew slightly larger and trade routes lengthened, the simple stick drawing became insufficient. There arose the need for a system that could be interpreted by someone who was not the map's creator. This introduced the necessary and very tedious concepts of scale and symbol. Imagine the long, slow, communal debate required to settle on a standard symbol. How should a perennial stream be distinguished from a dry creek bed? Perhaps a continuous line versus a dashed line. How should a village of 20 huts be drawn differently than a single shepherd's lean-to? Perhaps a small circle versus a single dot. The agreement on these symbols was a milestone in intellectual quietude. It wasn't a sudden, dramatic discovery, but a slow, boring cultural consensus, a quiet, general acceptance that from now on, this particular shape means this particular thing. The simplicity of the symbol became a comfort, a universal key to unlock the information held in the drawing. Early tools, the quiet geometry of sticks and string. The refinement of these early concepts required simple tools of measurement. The most common was simply string or rope, used to establish straight lines and measure reproducible distances. Imagine the surveyor, not a scientist, but a practical tradesman, carefully knotting a length of fiber. Each knot represented a standard unit of measure, perhaps the length of his own arm or the span of his stride. To measure a field, he would simply walk it, carefully laying out and counting the knots on the rope. This work was repetitive, it was methodical, it was slow. It was perfectly suited for inducing a state of deep calm. The process involved anchoring, securing one end of the rope at a starting point, stretching, slowly, deliberately stretching the rope until it was taut, marking, placing a temporary marker at the far end of the rope, counting, moving the anchor point to the marker and incrementing the count. This continuous cycle of anchoring, stretching, marking, and counting was the quiet engine that drove early territorial knowledge. The sound of the rope settling on the ground, the gentle thump of the marker stone, the whisper of the counter's voice. These were the first sounds of organized geography. They speak to the profound, soothing predictability of measurement. The maps produced from this effort, scratched onto bone, wood, or simple clay, were the first silent repositories of collective spatial memory. They allowed the tribe to rest, knowing that the pathways to the essential resources had been recorded, externalized, and safely stored against the quiet, threatening pressure of forgetfulness. Allow the thought of that slow, repetitive measuring process to become the final, gently receding sound in your mind, the string being stretched, the count being whispered. As we move forward into the gentle darkness, we leave behind the soft, ephemeral lines drawn in the sand and turn our attention toward permanence, the desire to capture the world
not just for a moment, but for all time, led to the creation of the very first physical maps. These were not rolls of fine paper or silk tapestries. They were often heavy, crude, and deeply practical objects. Let us consider the quiet authority of the ancient clay tablet. The unexciting certainty of clay. In the region of Mesopotamia, which is now modern Iraq, the earliest known forms of permanent writing and drawing were etched onto tablets made of damp clay. These tablets were then baked, becoming durable, hard objects, repositories of information designed to last for millennia. Among these surviving records, we find some of the very first maps. The most famous example is often the Babylonian map of the world, though other smaller tablets detail local fields and property lines. Imagine holding one of these tablets. It is not smooth. It is heavy. The edges might be slightly uneven. The map itself is not a sprawling artistic vision, but a simple, deeply symbolic representation. On the Babylonian map, the world is depicted as a flat circle, bordered by a swirling ring of water, which they referred to as the Bitter River. Within that central circle are recognizable shapes: the city of Babylon itself, the winding line of the Euphrates River, and surrounding marshes. The drawing is minimalist: a small number of circles, short strokes, and carefully incised cuneiform script. The lines are not precisely scaled, they are representative. The primary function of this map was not to navigate, but to convey a cosmological and political certainty. This is our world, and we are at the center of it. This map offered a deep, quiet comfort to those who looked upon it. It stated without shouting that their known universe had defined boundaries, and that within those boundaries life was ordered and comprehensible. Limitations and symbolic representation. The earliest lines drawn were constrained by the very material they were etched upon. The clay tablet, unlike parchment, did not allow for fine detail or vast scope. It dictated simplicity. Because of these material limits, the cartographers had to rely heavily on symbols and abstraction. A mountain was not drawn with shading and texture, but as a series of simple overlapping semicircles, like scales on a fish. A major settlement was often just a geometric shape, such as a square or a circle, labeled with a brief inscription. This simplicity of form is immensely soothing. It removes the visual chaos of reality and substitutes a peaceful, abstracted order. There is no urgency in these lines. They are permanent, but static. They merely exist, defining boundaries of property, resources, or known territory with a quiet, undeniable finality. Think of the steady, silent pressure applied to the stylus, pushing down into the soft clay to form a line that will endure for thousands of years, a slow, meditative act of creation. The quiet geometry of sticks and shells. Moving to different cultures, we find map forms that are equally ingenious, yet physically simpler. Consider the stick charts developed by the navigators of the Marshall Islands in the Pacific Ocean. These are perhaps the most profoundly abstract maps ever created. They were not made of heavy clay, but of light, flexible strips of coconut midrib and cowrie shells tied together with fiber. They do not resemble a modern map in any way. The sticks themselves represented the swells of the ocean, the patterns of wave refraction as they bent around islands. The small shells were placed at key intersections to represent the islands themselves. These charts were not used while sailing. They were studied ashore, memorized, and placed aside. They contained pure, abstract wave knowledge. They were not maps of what is seen, but maps of what is felt, the subtle, predictable rhythm of the ocean surface. The experience of reading these charts must have been one of complete, internalized calm. The navigator had to translate the abstract geometry of the sticks into the physical, felt motion of the canoe on the water, a gentle, quiet blending of the theoretical and the sensory. Pondering the edge, terra incognita. Every map, no matter how small or large, has an edge, and beyond that final drawn line lies the unknown, the edge of the known world. The quiet contemplation of this boundary is perhaps the most fascinating part of early cartography. It required the cartographer to make a choice, to leave the space blank, indicating a lack of data, or to fill the space with theoretical or symbolic representations. On many early European maps, the edges of the world began to be filled with illustrations of what they believed or feared lay beyond the defined boundaries. These were not always scary figures, but sometimes merely symbolic warnings, vast, swirling seas that symbolized the danger of the deep ocean, or fantastical creatures that represented the unknown nature of distant lands. These additions, though dramatic in content, were often drawn with a meticulous, careful hand. They served as a boundary marker, a visual whisper that said, "Here is the limit of our quiet certainty." The area often labeled terra incognita, unknown land, or simply left as a vast, unmarked void, provided a philosophical blank space. It was a place for the mind to rest, knowing that the responsibility for knowing every corner of the world had officially ended at that line. A comfortable, final surrender to the vastness of the unexplored. Allow your mind to drift toward that final soft border of the map, where the known facts give way to the gentle, endless silence of the sea, or the quiet, untrodden vastness of the unknown land. As we journey further into the past, we encounter one of the quiet, pivotal moments in the history of measurement. This is a story not of great battles or passionate discovery, but of patient observation, geometry, and a very deep well. Please settle and allow the details of this slow, ancient calculation to drift softly over your awareness. The gentle geometry of the Earth. Around the year 240 BCE, there lived a scholar named Eratosthenes. He was a quiet, meticulous man, serving as the chief librarian at the Great Library of Alexandria in Egypt. His work was not loud or urgent. It involved cataloging, archiving, and the careful study of scrolls. Eratosthenes, like many educated people of his time, already understood a foundational truth. The Earth was not flat. It was a sphere, a vast, quiet globe suspended in space. The question that occupied him was not if the Earth was round, but how large was that gentle curve? What was the measurement of its circumference, the distance around its entire surface? To solve this, Eratosthenes used a method that was supremely elegant and wonderfully boring in its technical simplicity. He needed three pieces of information. 1, a precise, fixed point of time. 2, a measurement of shadow. And 3, a measurement of distance. The fixed point of time, the summer solstice. Eratosthenes knew of a phenomenon that occurred in the city of Syene, which is now modern Aswan, far to the south of Alexandria. On one specific day of the year, the summer solstice, the midday sun shone directly down into a particular deep well in Syene. At that exact, silent moment, the sun was perfectly overhead. If you looked down the well, you could see the sun reflected in the water below. There was no shadow cast by any vertical object in Syene at that precise instant. The sun's rays were perfectly parallel to the well's vertical walls. This provided the first necessary absolute reference point. In Syene, on the solstice, at noon, the sun was at the zenith. The angle of the sun's rays was 0. Imagine that quiet well in the dry heat, the stillness of the solstice midday, the sun's light plunging down straight and true, a moment of perfect, predictable alignment. The measurement of the angle in Alexandria. Now, Eratosthenes remained in Alexandria, far to the north of Syene. If the earth were flat and the sun's rays were perfectly parallel, which they are due to the sun's immense distance, then when the sun was directly overhead in Syene, it should also be directly overhead in Alexandria. But Eratosthenes knew this was not the case. In Alexandria, when the sun reached its highest point on the summer solstice, vertical objects did cast shadows. The curved nature of the earth meant that Alexandria's surface was slightly tilted away from the sun relative to Syene. Eratosthenes set up a simple vertical pillar, a quiet, unadorned gnomon, and measured the length of its shadow at the moment the sun was directly overhead in Syene. This shadow measurement allowed him to calculate the angle of the tilt. He found that the angle of the shadow was 1/50th of a full circle. In geometric terms, this meant the angular difference between Syene and Alexandria was precisely 7.2 degrees. The difference in the shadow's angle was the proof of the Earth's curve between the two cities, a quiet, mathematical certainty. The measurement of the distance. The final essential step was the measurement of the linear distance between the two cities, Alexandria and Syene. This distance was measured using professional pacers known as bimatists, who were trained to walk with an extremely regular stride. The pace was their unit of measure. They walked the slow, hot, dusty path between the 2 points, counting their steps with meticulous, repetitive care. The distance was determined to be approximately 5,000 stadia. The exact length of the stadium unit varies today, but the number itself is the key. 5,000 units of measure. The entire process relied on this slow, repeated counting of paces across the long, flat Egyptian landscape, step after step, a methodical, unhurried collection of data. The final calculation, a slow division. Eratosthenes now possessed all the necessary components for the calculation. He knew that the 7.2-degree angle of the shadow was generated by the 5,000 stadia arc of the Earth's surface between the two cities. Since 7.2 degrees is 1/50th of the full 360-degree circle, 360 divided by 7.2 equals 50. He deduced that the arc distance of 5,000 stadia must represent 1/50th of the Earth's total circumference. The final, quiet calculation was a simple multiplication. 5,000 stadia multiplied by 50 equals 250,000 stadia. This number, 250,000 stadia, was his calculated circumference of the Earth. When converted to modern kilometers or miles, this ancient calculation is stunningly accurate, off by only a very small percentage from our modern satellite-verified measurements. This story offers deep comfort in its simplicity and reliance on reproducible observation. No complex machinery was required, only patience, geometry, a stick, and a very deep well. Allow the thought of that simple geometric ratio, the gentle curve of the Earth over a known distance, the sun, the shadow, the well, and the rhythmic soft pace of the counter.
Let us now consider the man who quietly formalized the system of global coordinates that would influence cartography for over 1,400 years. We speak of Claudius Ptolemaeus, known simply as Ptolemy, a Greco-Egyptian scholar living in Alexandria during the 2nd century of the Common Era. Ptolemy was not an explorer, he was not a sailor, he was a collector and an organizer. His great work, titled Geographia, or the Geography, was less a map and more a long, comprehensive, and ultimately soothing ledger of numbers. His contribution was the creation of a systematic, logical framework for mapping the world, entirely based on the steady, unchangeable principles of geometry and arithmetic. The systematic grid, latitude and longitude. Ptolemy's first and most profound act of quiet authority was the standardization of the two great coordinate axes, latitude and longitude. He accepted the concept of the Earth as a sphere and saw that for any location on that sphere, two pieces of numerical data were required to fix its exact position, no more, no less. Latitude was measured horizontally, north or south, from the central 0-degree line, the equator. Ptolemy divided the arc of the sphere from the equator to the pole into 90 equal degrees. This was based on the simple, reliable observation of the length of the midday shadow, just as Eratosthenes had used. The longer the shadow, the higher the latitude, a gentle, predictable relationship. Longitude was the perpendicular measure. This was measured vertically, east or west, around the circumference of the Earth. This measurement was more difficult for him, as it required accurate timekeeping or astronomical observations of lunar eclipses, which were rarely precise. However, Ptolemy systematically divided the circumference into 360 degrees, a number derived from the Babylonian sexagesimal system, which we still use today. 360 equal divisions wrapping neatly around the globe, a comforting number, divisible by so many factors. The entire surface of the known world was now quietly subject
to this network of invisible mathematical lines. The concept of zero, the arbitrary meridian. To measure longitude, Ptolemy needed a starting point, a vertical zero line, or prime meridian. This choice was arbitrary and based on the limits of his known world. He chose the westernmost point of the oikumene, the inhabited world, the islands known as the Fortunate Isles, often identified with the Canary Islands. This choice was practical. By placing the zero line at the western edge of his knowledge, all other locations he catalogued would have a positive, easterly longitude number. It avoided the inconvenience of negative numbers, simplifying the tables. Imagine the quiet geometric necessity of this decision. Where on an endless sphere do you decide to begin the count? Ptolemy simply stated, "We will begin here." This pre-Greenwich meridian served as the quiet, fixed baseline for all map reference for centuries. The authority of the tables, repetitive data. The true heart of Ptolemy's Geographia is not the 8 surviving maps, but the thousands of lines of sheer, unexciting numerical data. The work is essentially a vast 2-column spreadsheet listing the latitude and longitude for over 8,000 different locations. These include cities, river mouths, mountain peaks, and coastline indentations spanning from the British Isles to the far reaches of Asia. Imagine the methodical, repetitive work of compiling this list, a slow transcription of data points gathered from Roman itinerary records, travelers' accounts, and simple astronomical observations. The text reads like a lengthy, soporific litany of places and numbers. For example, the quiet entry for a major city might look like this: Alexandria, latitude 31 degrees, longitude 60 degrees. Rome, latitude 41 degrees 50 minutes, longitude 37 degrees 40 minutes. The mouth of the Indus River, latitude 24 degrees, longitude 106 degrees. Each entry is a 2-part code, a fixed coordinate, a precise numerical address for a place on the curved surface of the Earth. There is no drama in this data. There is only the quiet, unrelenting certainty that for every named place there exists a corresponding pair of numbers. The entire world reduced to a methodical, predictable index. The legacy of error and order. Ptolemy's work was not perfect. Many of his distance measurements for longitude were significantly compressed, making the known world appear much smaller than it actually was. For instance, he greatly underestimated the circumference of the Earth and overestimated the width of Eurasia. However, the system he established was flawless in its logic. The errors were not in the framework, but in the data he collected. The beauty of the Ptolemaic system was its reproducibility. Anyone who wanted to draw a map based on his coordinates could follow his quiet, simple instructions. 1. Draw the 360 degrees of longitude. 2. Draw the 180 degrees of latitude. 3. Place the point at the intersection of the 2 listed numbers. This was the quiet triumph of Ptolemy. He gave the world a permanent numerical language to talk about place. He reduced the complex, fluid reality of geography into series of calm, digestible digits. allow the thought of those intersecting silent numerical lines, the methodical counting of degrees, the fixed reference point of the equator, the absolute, unexciting predictability of a numerical grid. We now move forward in time, from the abstract coordinates of Ptolemy into the practical, lived reality of the medieval Mediterranean Sea. Here, a new kind of map emerged, one utterly concerned with certainty and safety. These are the Portolani charts, and their purpose was profoundly unexciting, simply to get a ship from one harbor to the next harbor without incident. Settle in, and let us gently study the quiet, functional beauty of these navigational tools. Practicality over philosophy. The Portolani charts, which began to appear widely in the 13th century, were a complete departure from the ancient theoretical world maps. They were not concerned with the circumference of the Earth or the alignment of the stars. They focused exclusively on the coastal edge, the complex, curving margin where land meets water. They are named after the Portolani, detailed written sailing directions or pilot books that preceded them. The map itself was a visual index to these dry, sequential instructions. Imagine a sailor unfolding one of these charts on a table in a quiet cabin. The chart is typically drawn on a single, large sheet of vellum, animal skin, stretched taut and flat. It is immediately striking because it looks profoundly technical and deeply ordered. The chart's primary concern was coastal fidelity. The coastlines, particularly around the Mediterranean, the Black Sea, and the Atlantic seaboard, were drawn with meticulous, almost obsessive detail. Every small indentation, every bay, every headland was carefully rendered. The names of hundreds of small harbors and ports, often written perpendicular to the coast, form a dense, silent commentary on the accessibility of the shore. This level of detail offered a deep, quiet assurance. It confirmed to the sailor that the coastline, however complex, was known, charted, and entirely predictable. The gentle intersections, rhumb lines. The most defining and perhaps most soothing feature of the Portolani charts is the dense, web-like network of rhumb lines that covers the entire surface. A rhumb line, also known as a line of constant compass bearing, is essentially a straight line drawn from a central point of the compass. These charts did not use the grid of latitude and longitude. Instead, they used a series of large, centrally located compass roses. From these central roses, 32 lines radiated outward, representing the 32 points of the compass, north, northeast, east, etc. Imagine placing your gaze upon the center of the chart. From that point, the lines flow outward like the spokes of a wheel. Then the lines from the neighboring compass roses are drawn, intersecting the first set. The result is a vast, crisscrossing network of straight lines. This lattice of lines was not arbitrary. It represented every possible, constant direction a ship could sail in. To navigate, the sailors simply found the line that ran closest to their intended destination and set their course based on that line's direction. The beauty of the rhumb line system for deep sleep is its redundancy and repetition. The lines repeat across the entire surface of the vellum. Straight line intersecting straight line. a pattern that speaks only of constant direction and measurable angle. There is no mystery in this web, only geometric certainty. The practical purpose, harbor to harbor. The Portolani charts were designed for dead reckoning, a method of navigation that relies on calculation of distance run and compass bearing. Their purpose was narrow and entirely practical, safe travel between two known points. The calculation was simple and therefore predictable. 1. Read the angle. The sailor identifies their current harbor, A, and their destination harbor, B. They lay a ruler parallel to the closest rhumb line connecting A and B. 2. Determine distance. They use a pair of dividers to measure the distance between A and B against a simple scale printed on the chart. 3. Set course. The compass bearing determined by the rhumb line is read, and the ship is steered along that angle. The entire process bypasses the need for complex spherical trigonometry or celestial mechanics. It is grounded, simple, and repeatable. The charts provided the comforting knowledge that the journey from, say, Genoa to Tunis or Marseille to Majorca had been calculated, charted, and reduced to a straight line of constant bearing. This sense of operational simplicity and fixed purpose is deeply calming. The complex world of the open sea is momentarily tamed by a dense, practical network of predictable lines. Allow yourself to focus on the soft, repeated sound of the water lapping against the hull, and the quiet, ordered certainty of the 32 lines intersecting on the vellum, defining every possible, predictable direction.
Let us now drift gently away from the sea itself and travel inland to the quiet, cool solitude of the scriptorium. This was the heart of knowledge retention, where the great works of the past and the essential maps of the present were slowly and meticulously brought into physical being. We are observing the cartographic scribe, a figure defined by patience and a profound tolerance for repetition. This work was not fast. It was an act of quiet, almost motionless dedication, often performed by a single individual over many months. Settle in and listen to the faint, steady sound of the quill on the page, the constant rhythm of a mind focused entirely on the line. The preparation, the silent vellum. The foundation of any great medieval map was not paper, which was expensive and fragile, but vellum, a specialized prepared animal skin. The preparation of this material was the first slow ritual of creation. The hides, usually from calf, kid, or lamb, had to be cleaned, treated, stretched, and repeatedly scraped. Imagine the steady, rhythmic effort required to stretch the damp, raw hide onto a wooden frame or hearse. The edges were slowly pegged, tension applied, then left to dry. The goal was to create a thin, smooth, and uniformly white surface. This demanded hours of quiet, focused scraping with a crescent-shaped knife called a lunellum. The scribe or preparer had to scrape away any remaining hair or fat, gently, evenly, to ensure the vellum did not tear or become too thin in any one spot. Listen to the very soft, subtle swooshing scrape of the blade against the hide. A long, smooth stroke, then another and another. This sound of preparation is the sound of the world being quieted and made ready to receive the lines of the map. Once dried, the vellum possessed a creamy, opaque quality. It was a resilient surface that could absorb ink without running and endure the heavy application of colorful pigments. It was a surface built for longevity, a material designed to quietly outlast the century in which it was created. The chemistry of color, grinding the pigments. Before the map could be drawn, the colors had to be mixed. This process was far removed from the modern convenience of pre-mixed tubes. It involved the slow, patient grinding of raw earth, minerals, and natural compounds. The scribe required small, sturdy bowls and a heavy muller, a smooth glass or stone tool to crush the raw materials into fine, consistent powders. Consider the composition of the basic palette. Black ink, usually made from soot or charcoal mixed with gum arabic and water. The grinding had to be continuous until the particles were so fine they suspended perfectly in the liquid, creating a dark, steady line. Earth tones, browns and yellows, sourced from various clay pigments such as ochre. This required gathering the soil, cleaning it, and then the repetitive, rhythmic motion of grinding it to a silky smooth dust. Greens, often made from mineral compounds such as verdigris. These required careful, delicate handling, as the chemical structure could be unstable. The act of grinding was meditative. A steady, circular pressure applied to the muller, back and forth, for long, quiet periods. The sound of stone softly scraping stone, the faint earthy scent of the powder rising, the focused attention required to avoid gritty imperfection. Each color was a small triumph of slow, simple chemistry. Once mixed with a binder like egg white or glaire, it was ready to be gently applied to the waiting vellum. The meticulous application, drawing the invisible grid. The cartographic work began with the quiet imposition of order. The scribe did not simply start drawing coastlines. They first drew a faint, underlying framework. Even on portolan charts, which did not use official latitude and longitude, the scribe would first use a ruler and a stylus to prick tiny, near-invisible holes in the vellum. These pricked points would then guide the ruler in drawing the faint, pencil-thin lines that formed the rhumb line network, the geometric web we studied in the last chapter. These initial lines were often drawn in a very dilute, pale ink, or even with a lead point, to ensure they could be quietly hidden by the final colors. This preliminary work of drawing the invisible grid was perhaps the most crucial stage. An error here meant the entire map was flawed. The scribe hunched over the smooth vellum, moved the ruler slowly, carefully pressing the lead point to ensure a perfectly straight line connected two far-off points. No rushing was permitted. Every measurement was checked twice, and then executed with a steady, unhurried hand. The final detail, filling the void. Once the framework was secure, the coloring began. This was the process of filling the vast, white spaces with recognizable form. The scribe would use tiny, specialized brushes, often made from squirrel hair, to apply the pigmented wash. Imagine the slow process of coloring a mountain range. applying the earthy brown pigment carefully along the contour line, then allowing it to dry completely before adding a thin, precise line of black to define the peak's edge. The details of the towns, the compass roses, and the coats of arms were painted with the greatest concentration. Each miniature church spire, each flag, each small symbolic representation of a trading vessel required a few perfectly controlled strokes. This was a profoundly isolated labor. The world outside did not matter. Only the careful, detailed conversation between the scribe, the brush, and the quiet resilience of the vellum. It is the sound of deep, focused calm.
We now arrive at a problem that haunted the great intellectual minds of the 17th century, a difficulty so persistent, so quietly frustrating, that its solution became the ultimate quest of measurement. We speak of the longitude problem. It is important to remember that at this stage of history, the challenge was not finding latitude. Latitude, the north-south position, could be found reliably and simply by measuring the altitude of the sun at noon, or the fixed altitude of the pole star at night. These were certainties. Longitude, the east-west position, was the great quiet void. Settle in and let us explore the dry, theoretical concepts that slowly, inevitably, failed to solve this monumental challenge. Longitude as a calculation of time. The problem of longitude is fundamentally a problem of time. This principle is simple, unexciting, and mathematically unyielding. The Earth completes one full rotation of 360 degrees every 24 hours. This means that for every single hour that passes, the Earth rotates 15 degrees of longitude. Therefore, the longitude of any location on the Earth can be determined simply by knowing the precise time difference between that location and a fixed reference point, the prime meridian. For example, if a ship sets sail from London and its local time is 3 hours behind London time, the ship must be 45 degrees of longitude to the west. 3 multiplied by 15 equals 45 degrees. The formula is clear. The mathematics are simple. The execution was nearly impossible. The challenge was not the math, but the timekeeping. A perfect clock, one that could keep Greenwich time, or whatever prime meridian was chosen, perfectly, despite the ceaseless motion of the ocean, did not exist. The failure of the first hypothesis, magnetic variation. One of the earliest and quietly appealing theoretical solutions involved using the Earth's magnetic field. The hypothesis was simple. If the magnetic compass always points toward a magnetic North Pole, and if that magnetic pole stood in a fixed, predictable relationship to the true geographic North Pole, then the difference between the two, the magnetic variation, should be consistent and chartable. The hope was that for any given point on the Earth, the measured magnetic variation would correspond to a single, unique line of longitude, a vast, invisible grid laid down by the planet's own magnetic properties. Navigators spent many quiet decades meticulously recording their compass readings and comparing them to their observed astronomical north. The result of this steady, repeated data collection was the slow, predictable dissolution of the hypothesis. The magnetic variation did not behave predictably. It changed gradually over time, a phenomenon known as secular variation. It also varied locally, being affected by large land masses or deep ocean trenches. The magnetic field was and is a complex, ever-shifting entity. The data, when compiled, did not reveal a clean numerical pattern. It revealed only a confusing, unpredictable web of subtle difference. The quiet hope that the Earth itself would provide a fixed magnetic clock slowly and inevitably faded into the background of discarded theory. The problem remained unsolved. The lunar solution: excessive calculation. The most serious and mathematically dense proposed solution was the method of lunar distances. This was not a physical clock, but an astronomical clock. The moon is the fastest moving object in the night sky. Its position changes constantly relative to the background stars, a motion that is observable and, more importantly, predictable. The theory stated that if an observer at sea could measure the precise angle or distance between the moon and certain fixed bright stars, they could use this measurement to determine the exact time at the prime meridian. Since the moon's predicted position was catalogued in official tables for every hour of the year, the measurement at sea could be translated back to the standardized time in London. The theory was sound. The execution was technically arduous and supremely boring in its complexity. Imagine the sailor on the deck trying to sight the moon and a star through a brass instrument, the early quadrant or octant, while the ship pitched and rolled. The physical difficulty of the observation was immense, but the real mind-numbing challenge lay in the calculation that followed the observation. The raw measurement taken at sea had to be cleared. This meant adjusting the observed angle to account for numerous atmospheric, parallax, and refraction effects. It was a dense sequence of complex spherical trigonometry involving pages of dry numerical work. It required 1. Correction for the ship's actual horizon, 2. Correction for atmospheric refraction, the bending of light, 3. Correction for the moon's parallax, the apparent shift in its position due to the observer's location on Earth. These calculations were long, repetitive, and required the use of massive logarithmic tables. A single calculation to clear the distance and find the prime meridian time could take a skilled mathematician 2 to 4 hours of continuous, quiet arithmetic. This method was theoretically perfect, but practically impossible for the average overworked navigator to perform accurately during the stress of a long voyage. It demanded too much precision, too much silent time spent with numbers, too much meticulous calculation. The solution was there, but it was buried under an intimidating mound of tedious mathematics. The slow, steady, quiet ticking of the theoretical clock remained the goal, the simple, perfect answer hidden by the complexities of the physical world. Allow the thought of those complex calculations, the silent turning of the pages of logarithms, and the endless, measured ticking of time to guide your mind into a state of deep, unhurried rest. We now arrive at the most famous and perhaps the most geometrically fascinating of all map structures, a structure that quietly dominates the visual understanding of our planet. We speak of the Mercator projection. This projection was conceived by the Flemish cartographer Gerardus Mercator in the year 1569. His purpose was not artistic or philosophical, but entirely meticulously practical. He sought a map that would allow a ship to maintain a constant compass bearing and thus follow a straight line from one point to another, anywhere on the globe. To achieve this, he had to perform an elaborate conceptual act of mathematical flattening. Settle in and allow your mind to trace the slow, steady lines of how a curved surface is mathematically transformed into a perfect rectangle. The fundamental problem, the unavoidable stretch. The core, unyielding problem of cartography is that the surface of a sphere cannot be mathematically converted into the surface of a flat rectangle without distortion. It is impossible to flatten an orange peel without tearing or stretching it. The Mercator projection addresses this problem by defining precisely how that inevitable stretching will occur. It is classified as a cylindrical projection. Imagine the Earth as a perfect, quiet globe. Now, conceptually wrap a large cylindrical sheet of paper around the globe. This cylinder is placed tangent to the Earth, meaning it only touches the Earth at one single horizontal line, the equator. The transformation process involves projecting every single point on the spherical surface outward onto the inner surface of that surrounding cylinder. Once every point is mapped, the cylinder is conceptually cut vertically and then unrolled to reveal the final flat rectangular map. This process ensures that the resulting map is a neat, perfectly formed rectangle. The entire circumference of the equator now matches the length of the top and bottom edges of the map. The straightening of the meridians, the longitude. Let us first examine the lines of longitude, the north-south lines, or meridians, that run from pole to pole. On the real spherical Earth, the lines of longitude are not parallel. They start at zero width at the North Pole and gradually widen until they are maximally spaced at the equator, before narrowing again to zero width at the South Pole. They converge silently at the two extremities. However, when these lines are projected onto the cylinder and the cylinder is unrolled, a critical transformation occurs. The vertical lines of longitude are forced to become perfectly straight and perfectly parallel. They never converge. This means that the distance between the meridians, which should narrow as you travel north or south, remains fixed across the entire map. The distance between 0 degrees north latitude is exactly the same as the distance between the meridians at the equator. This is the first essential distortion of the projection. This process provides immense geometric satisfaction. All longitudinal lines become simply straight, parallel, and equally spaced, an elegant, predictable rhythm of vertical reference. The exponential stretch of latitude. The maintenance of the parallel longitude lines forces the projection to stretch the lines of latitude, the east-west parallels. This is the true monotonous elegance of the Mercator system. To compensate for the fixed, straight longitude lines, the horizontal lines of latitude must be placed at ever-increasing intervals as they move away from the equator. The distance between 0 degrees equator and 10 degrees north is a specific, measurable unit. The distance between 10 degrees north and 20 degrees north is slightly greater. The distance between 50 degrees north and 60 degrees north is significantly greater. The distance between 80 degrees north and 85 degrees north is vastly, exponentially greater. The mathematical requirement is that the amount of vertical stretching must be precisely equal to the amount of horizontal stretching. This ensures that the map maintains conformality, meaning that the shape of any small feature, like a small island or a harbor outline, is preserved, even though its size is wildly inaccurate at the poles. Imagine a single small square placed near the equator. Now conceptually move that exact same square toward the North Pole. As it moves, the Mercator projection dictates that the square must grow larger and larger on the map, stretching both horizontally and vertically, maintaining its perfect square shape, but losing all fidelity to its actual scale. The poles themselves, the single fixed points of north and south, cannot be mapped at all. To plot them would require an infinite vertical distance as the stretch approaches infinity. They are simply not shown. The map silently stops short of the true extremities of the Earth. The practicality of the straight course, loxodrums. The single unexciting purpose of all this complex geometry is the creation of the rhumb line, or loxodrum, as a straight line. On a spherical Earth, a line of constant compass bearing, a rhumb line, is a spiral that gradually approaches the pole. It is a long, gentle curve. However, because the Mercator projection maintains the perfect right-angle relationship between the compass direction, longitude, and the direction of the parallels, latitude, any line of constant bearing drawn on the map is represented as a perfectly straight line. This was the quiet triumph of Mercator. To plot a course from Europe to the Americas, the navigator simply drew a ruler straight line between the starting point and the destination. The direction of that line, the angle it crossed the parallel meridians, was the constant compass bearing the ship had to maintain. This conversion of a complex three-dimensional spiral course into a simple two-dimensional straight line was the pinnacle of practical geometry. It replaced complex repetitive calculations at sea with the simple straight edge of a ruler. Allow the thought of this relentless mathematical stretching to settle your mind. The lines of latitude pulling further and further apart, the meridians standing perfectly parallel, an elegant, necessary distortion providing the ultimate comfort of the straight line.
We now descend from the high, abstract mathematics of Ptolemy and Mercator down to the quiet, rolling surface of the Earth itself. We transition from theory to the arduous, on-the-ground reality of surveying. This chapter concerns the systematic process used by nations to create their own internal, precise maps, the foundation of all modern property lines and infrastructure planning. This work was known as National Grid Surveying, and it was defined by meticulous care and immense duration. Settle in and allow your mind to trace the soft paths of the surveyors as they attempt to impose perfect geometry upon the imperfect curves of the physical world.
The necessity of the baseline. For a nation to create a precise map of its territory, every measurement must begin with one single certain fact: a known, accurately measured distance. This distance is called the baseline. All other distances on the map, no matter how vast or remote, are ultimately derived from this one humble line. Imagine the enormous silent pressure placed upon the surveyors responsible for establishing this initial line. If the baseline measurement was off by a single inch, that error would slowly compound, expanding into dozens of feet of error across the full expanse of the country. Therefore, the measurement of the baseline was one of the most painstaking, slow, and repetitive tasks in all of historical science. The slow pace of the measurement. The chosen baseline was typically a flat, level stretch of land several miles in length, often near a quiet coastline or an ancient Roman road. The goal was to eliminate any vertical irregularity. The surveyors did not use simple rope. They used specialized, rigid measuring devices, often long iron or glass rods or precise chains. Imagine the process. 1. Setting the rods. A team of surveyors would carefully lay the first measuring rod end to end on the ground. 2. Leveling. They would use sensitive spirit levels to ensure the rod was perfectly horizontal. Any slight slope had to be corrected for mathematically or avoided completely. 3. Marking the end. Once the first rod was perfectly positioned, a second surveyor would gently set a precise marker, a small pin, or a fine point exactly where the rod ended. 4. Advancing. The first rod was then carefully moved ahead to start exactly at the marker pin, and the process began again. This continuous cycle of laying, leveling, marking, and moving often had to be repeated thousands of times over the entire length of the baseline. The work was typically done at night or during still, cloudy days when temperature fluctuations were minimal. Why? Because metal and glass rods expand subtly with heat. Even a small increase in temperature could stretch the baseline by a fractional but unacceptable amount. This demanded patience and a quiet acceptance of the weather's constraints. The process was slow, methodical, and profoundly unexciting. The geometric certainty, triangulation. Once the baseline, the one single known distance, was established, the surveyors were ready to employ the principle of triangulation. Triangulation is based on a simple, comforting rule of geometry. If you know the length of just one side of a triangle, and you know the precise angles of all three corners, you can mathematically determine the lengths of the other two sides without ever having to walk or measure them. The National Survey did not measure distance directly. It measured angles. From the two ends of the baseline, A and B, the surveyors would identify a prominent distant landmark, C, a hilltop, a tower, or a specially constructed signal post. This created the first foundational triangle, ABC. Using highly precise instruments known as theodolites, the surveyors would quietly measure the angle at A and the angle at B, pointing toward the remote point C. With the known length of side AB and the measured angles at A and B, the lengths of sides AC and BC could be calculated with perfect geometric certainty. The beauty of this method lies in its efficiency and its silent reliance on mathematics. Once the first triangle was solved, side AC now became the known side for a new triangle, ACD, and side BC became the known side for yet another, BCE. Building the national grid, a slow expansion. The entire nation was mapped by repeating this process, triangle by triangle. The surveyors did not need to measure distance again for hundreds of miles. They simply needed to find high points, often called trig points or triangulation stations, and measure the internal angles of the triangles they formed. This required immense organizational patience. Imagine the landscape covered in these quiet, invisible triangles. They were not drawn on the ground, but only existed in the surveyor's notebook calculations. The work was relentless. 1. Setting station. Climbing a remote hill and setting up the heavy, brass theodolite instrument on a tripod, ensuring it was perfectly level. 2. Sighting. Slowly, painstakingly turning the telescope to sight the distant signal post on the next hill, often miles away, and recording the angle to the nearest fraction of a second of arc. 3. Repetition. Repeating the sighting process multiple times to ensure the accuracy of the angle. 4. Moving on. Packing up the heavy instrument and moving, often slowly and silently, to the next remote hilltop. The entire map of the country, the entire national grid, grew outward, slowly and inevitably, from that single, precisely measured baseline. It was an epic, silent undertaking that took decades to complete, requiring immense stillness, concentration, and a quiet faith in the unyielding laws of plane geometry. Allow the thought of those perfect invisible triangles spanning the vast, uneven landscape to settle your mind. The simple geometry imposing order on the physical world, one precise angle at a time.
In the previous chapter, we observed the vast, silent geometry of the National Survey. Now we must focus intently on the humble, practical tools that made this great geometric effort possible. The quiet heroes of precision, the theodolite and the Gunter's chain. These instruments were not loud or dramatic. They demanded respect, maintenance, and an unwavering commitment to careful, repetitive labor. Settle in and allow the details of their slow, measured function to guide your thoughts into stillness. The theodolite, a study in brass and glass. The theodolite is the primary instrument used for measuring the precise horizontal and vertical angles required for triangulation. It is a beautiful, complex object, usually crafted from finely machined brass, containing lenses, mirrors, and highly sensitive leveling devices. Imagine the surveyor carefully removing the instrument from its protective wooden case. It is heavy, cold, and demands immediate attention. The first essential process before any measurement can be taken is leveling. This is perhaps the most repetitive and patient part of the entire survey. The theodolite must be placed on a sturdy tripod and then brought to a state of perfect horizontality. This is achieved using 3 small adjustable screws at the base of the instrument and a highly sensitive spirit level, a bubble
suspended in a sealed glass tube. The surveyor must repeatedly turn one screw, observe the bubble's subtle shift, turn the next screw, observe the bubble again, and then repeat this sequence over and over until the bubble rests precisely in the center of its marked guides in all directions. The process is slow. It is meticulous. It requires immense stillness of hand and mind. Any impatience, any rushed twist of the screw, and the bubble glides away from the center, demanding a restart. It is a quiet, continuous conversation between the surveyor and the unyielding physics of the bubble. Only when the instrument is perfectly level can the surveyor begin the slow work of sighting and recording the angles that form the foundation of the map. The art of sighting and recording. Once leveled, the surveyor slowly rotates the telescope of the theodolite to focus on a distant marker, perhaps a signal light or a flagpole, many miles away. The rotation of the instrument turns a finely etched glass circle inside the housing, which is marked in degrees, minutes, and seconds of arc. The surveyor must read this angle through a magnifying eyepiece, recording the measurement in a heavy, bound notebook. The act of sighting demands total stillness. The surveyor must gently touch the focus knob, wait for the image to clear, and then read the exact number. This reading is often repeated 6 to 12 times for every angle, turning the instrument slightly between each set to eliminate small human errors. The final true angle is an average of all these separate repetitive readings. This painstaking effort ensured that the margin of error in the national survey was reduced to mere fractions of a second of arc, a degree of precision that is both impressive and perfectly soporific. The Gunter's chain, a legacy of repetitive distance. While the theodolite measured the angles for the large invisible triangles, the Gunter's chain measured the short, essential distances for property lines and for the original baseline. Invented in the 17th century by Edmund Gunter, this was the standard physical unit of distance measurement for centuries. The chain was precisely 66 feet long. This seemingly arbitrary length was chosen because 10 square chains equaled exactly 1 acre, a useful, simple relationship for land taxation and farming. The chain was composed of 100 individual iron links connected by 3 rings each. 100 links, 66 feet. This gave the chain the ability to measure distances easily in decimals. Imagine the team of 2 chainmen working their way slowly across a field. 1. The leader walks forward, pulling the chain taut until its full 66-foot length is reached. The follower calls out, "Chain." The leader pushes a small iron arrow, a pin, into the ground to mark the precise end of the chain. The follower moves up to that pin, holds the end of the chain steady, and the leader advances again. The follower picks up the pin. The total distance is found by the number of pins collected by the follower. This was a long, slow dance of laying, pulling, marking, and counting. The process was endlessly repetitive. Pin down, chain pulled. Pin up, chain pulled. The soft clinking and scraping of the 100 brass links against the dirt was the constant rhythm of distance measurement. The chain often grew subtly longer over time through the continuous friction wearing away the iron rings. This meant the chain itself had to be checked, cleaned, and repaired regularly, a quiet mandatory ritual of maintenance to preserve its precise legal length. The surveying tools were not just objects of science, they were objects of immense quiet dedication. They demanded slowness, stillness, and a belief in the comfort of predictable repetition. Allow the thought of those tiny, accurate movements, the bubbles settling in the glass tube, the metal links clinking softly, to soothe your mind. The perfect geometry created through repetitive physical effort.
We have traveled through the mind of the geometer and across the fields with the surveyor. Now we arrive at the final silent chamber of the map-making process, the workshop of the engraver. This is the place where the precise, hard-won numbers of the triangulation and the vast calculated geometry of the projection are translated into physical, reproducible lines. This is the stage where the map is permanently frozen onto a plate of cold, unyielding copper. Settle in and listen closely to the faint, steady whisper of the cutting tool, tracing the lines that will define the shape of our world for centuries. The copper canvas, preparing the plate. The engraver's canvas was not a flexible sheet of vellum, but a heavy, rectangular plate of polished copper. Copper was chosen for its ideal blend of hardness and workability. It was firm enough to hold a fine line, yet soft enough to be cut with steel tools. The preparation of the plate demanded immense initial care. The surface had to be perfectly flat and polished to a mirror shine. Any tiny scratch, dent, or imperfection would appear as a major flaw in the final printed map. Imagine the engraver working quietly, patiently, rubbing the surface with fine abrasives, checking the plate repeatedly under a low-hanging light. The goal was to eliminate all texture, creating a smooth, reflective void, ready to receive the map's entire complex reality. This polishing was a repetitive, smoothing ritual that set the tone for the entire process. Absolute dedication to the elimination of imperfection. The transfer, the reversed world. Before the cutting could begin, the surveyed data had to be transferred onto the prepared copper surface. This was done using a preparatory drawing, often traced onto the plate using a thin layer of wax or varnish that would resist the acid, though later plates were directly engraved. The critical and quietly demanding challenge of this stage was reversal. Because the copper plate would be used for printing, where the image is pressed onto paper, the map lines on the plate itself had to be drawn backwards, or in mirror image. The engraver had to mentally translate every single feature. Every river winding to the left must be etched winding to the right. Every town name, every figure of latitude or longitude had to be etched in precise, backwards calligraphy. This required a profound level of sustained mental discipline. The engraver could never relax their focus, as a moment's lapse would result in an entire region being printed backwards. This silent, constant mental effort, the necessity of seeing the world in reverse, is what defines the lonely artistry of the engraver's work. The tool and the line. The graver's song. The primary tool of the engraver was the graver, or burin, a simple, sharp steel rod with a shaped, diamond-like tip set into a wooden handle. The engraver did not scratch the surface. They actually pushed the graver into the copper, curling up a tiny shaving of metal called the burr as the blade cut a furrow. The depth and width of the line were entirely controlled by the pressure and angle of the engraver's hand. To represent a major river or a national border, the engraver would push the graver deeply and slowly, creating a wide, dark line that would hold more ink during printing. To represent a minor creek or a subtle contour line, the pressure was lightened, creating a fine, delicate line, a mere whisper of geography. Listen to the sound again, the tiny, sharp scrape of the steel against the copper. It is a slow, steady noise. The engraver's hand did not stop until the line was complete. The movement required immense stillness. The plate was often secured on a cushion, and the engraver manipulated the plate with one hand while pushing the graver with the other. The speed of the work was dictated by the tool's need for perfect control. A single complex section of coastline, meticulously detailed with hundreds of tiny harbors and capes, could take a week of continuous, silent labor. The detail of the graticule. The most tedious, repetitive, and essential work involved etching the graticule, the lines of latitude and longitude. These lines were not artistic. They were purely mathematical. They had to be etched perfectly straight and perfectly parallel to the borders of the plate for the Mercator projection. And they had to be perfectly consistent in thickness. The engraver would use specialized rulers and guides, slowly carving hundreds of identical parallel lines across the entire plate. Each line had to start and stop cleanly at the plate's border. The process was purely mechanical and mentally taxing in its demand for sustained precision. Imagine the engraver, hours into the night, carving line 57, then line 58, then line 59. Each line exactly matching the previous one. A long, quiet exercise in repetitive control. The copper plate was the final, hard translation of human knowledge. It held the geometry of the map, secured against change, ready to be reproduced countless times. A silent testament to the patience of the hand that cut the copper. Allow the gentle, focused scraping sound of the graver to smooth away any lingering tension. The stillness of the copper plate, the reversed lines of the world, the steady, perfect pressure of the dedicated hand. We have now examined the tools and the tireless human effort required to make a map, but let us return to the most important element of all, the grid. The vast, invisible network of lines that makes all maps possible. This network, known as the graticule, is composed of the lines of latitude and longitude. They are purely theoretical constructions, lines that do not physically exist on the Earth, yet they are the basis for all practical travel and organized knowledge. They are, in essence, an agreement. Settle in and allow your mind to contemplate the quiet beauty of these intersecting abstract lines, thin as gossamer, yet strong enough to hold the world still. The theoretical nature of the grid. The most soothing aspect of the graticule is its total independence from the physical world. A river may change its course, a mountain may erode, and a coastline may shift over centuries, but the lines of latitude and longitude remain fixed. The grid is imposed upon the Earth, not derived from it. It is a mathematical model, a quiet assertion of order over chaos. The lines of latitude are simple. They are the parallel circles that wrap around the globe equidistant from each other, running east to west. They measure the angular distance from the equator, 0 degrees. The lines of longitude are the meridians, the great half-circles that run north to south, converging precisely at the poles. They measure the angular distance from the prime meridian. This structure creates a perfect, predictable mesh of right angles, except at the poles. At any point where a line of latitude crosses a line of longitude, that point is fixed, permanently and universally. This geometric certainty is profoundly calming. The arbitrary nature of the 360-degree division. When we discuss the logic of the grid, we must acknowledge the fundamental arbitrariness of the numbers used. Why are there 360 degrees in a circle? Why are there 60 minutes in a degree and 60 seconds in a minute? This division traces its origins back to the ancient Babylonians, who used a base 60 sexagesimal number system. The 360-degree circle was likely chosen because 360 is a highly divisible number. It can be cleanly divided by 2, 3, 4, 5, 6, 8, 9, 10, 12, and so on. This mathematical convenience made calculations, like the one Eratosthenes used, much simpler to perform by hand. Therefore, the structure of the map is rooted not in planetary physics, but in ancient counting preference. Imagine the profound global agreement that had to take place over thousands of years to accept this arbitrary division as absolute truth. When a sailor reports their position as 40 degrees north, they are quietly paying homage to a mathematical choice made by people who lived 4,000 years ago. This slow, quiet acceptance, this global consensus on a system of numbers offers deep comfort. It suggests that humans, when facing the overwhelming complexity of the world, can agree on a shared, unexciting system of abstraction. The significance of the equator and the poles. The equator is the natural 0 point for latitude. It is defined by the Earth's rotation. It is the line exactly halfway between the north and south poles. Every point on the equator is equally distant from every other point on the equator. It is a line of perfect balance and quiet equilibrium. The lines of latitude flow outward from this 0, gaining degrees toward the poles, which are designated as the maximum points of 90 degrees north and 90 degrees south. The poles in this abstract system are points of total stillness and convergence. At the poles, all 360 lines of longitude meet in a single, silent location. This confluence of all lines into a single point is a satisfying geometric conclusion. Think of the equator as the perfect horizontal reference line, a point of rest, and the poles as the final vertical destinations, the limits of the geometric system. The quiet struggle for the prime meridian. While the equator was naturally defined, the prime meridian, the 0 point for longitude, was the site of centuries of quiet national disagreement. As discussed with Ptolemy, any meridian can technically be the 0-degree line. Historically, different countries used their own capital cities or prominent observatories as the starting point: Paris, Rome, Faro, and others. This multiplicity of 0 points led to constant, frustrating recalculations for sailors. A French map used one 0, a British map used another, and an Italian map used a third. The need for a single, quiet, global agreement led to the International Meridian Conference of 1884. At this conference, representatives from 25 nations quietly convened to decide where on the face of the earth the world should begin its counting. The decision was, in itself, profoundly boring. The meridian passing through the center of the transit instrument at the Royal Observatory in Greenwich, England, was chosen as the universal prime meridian. This choice was not made because of Greenwich's geographic significance, but because the British nautical charts were already the most widely used globally. It was a choice based on practical convenience and established repetition. Since 1884, every second of global time and every degree of longitudinal position has been quietly tethered to the steady, unchanging point of 0 degrees, 0 minutes, 0 seconds, passing through a specific, unexciting building in a London suburb. This final global agreement on the abstract grid offers the greatest psychological rest. The entire complex, fluid world is now held in place by two things: the natural balance of the equator and the quiet, agreed-upon location of a single meridian in Greenwich. Allow your mind to trace the lines of this silent, abstract grid, the perfect parallels of latitude, the converging lines of longitude, holding every point on Earth in a state of fixed, predictable rest.
We have successfully placed a point on the Earth's flat grid, using latitude and longitude. But the world is not flat. It is a surface of gentle rises, deep valleys, and slow, sloping plains. The final, quiet challenge of the cartographer is to represent the third dimension, elevation, onto the uncompromising surface of a two-dimensional map. This process involves translating the majestic, complex reality of mountains and hills into a language of simple lines, shades, and colors. Settle in and allow your mind to trace the quiet, invisible path of a line of equal height as it wraps slowly around the gentle curves of the landscape. The geometry of equal height, contour lines. The most precise and mathematically elegant method for representing vertical height is the contour line. This concept is profoundly simple, yet often requires careful, focused contemplation to fully appreciate. A contour line is a continuous line drawn on a map that connects all points of equal elevation above a fixed reference point, usually sea level. Imagine standing on a gently sloping hillside. If you were to walk along a path that neither went uphill nor downhill, a path of absolute, perfect levelness, the path you followed would describe a contour line. If you were to repeat this exercise 5 feet higher up the hill, and then 5 feet higher again, you would trace 3 separate, non-intersecting contour lines. The critical concept is the contour interval. This is the vertical distance between one contour line and the next. On any single map, this interval is fixed and unchanging. It might be 10 feet or 20 meters. This fixed interval provides a powerful, unexciting predictability to the entire system. The closer the contour lines are drawn together on the map, the steeper the slope is in reality. If the lines are far apart, the slope is gentle and gradual. If they are concentric circles, you are looking at a perfectly symmetrical hill or depression. Contour lines are deeply satisfying in their adherence to a few simple, unyielding rules. 1. They never cross. 2 lines of different elevation cannot occupy the same space. A single point on Earth cannot be both 50 feet high and 60 feet high simultaneously. 2. They always close. Every contour line will eventually close in on itself, either within the map boundaries or beyond them, as they represent a continuous circuit of elevation.
3, they indicate direction. When a contour line crosses a stream or valley, it always forms a V shape that points upstream, indicating the direction of the higher elevation. The work of plotting these lines in the field was immensely slow. The surveyor had to constantly use their instruments to find points of equal elevation, often moving horizontally across the hillside, confirming the height, and then moving to the next adjacent point of equal height. A careful, continuous horizontal crawl across a vertical surface. The repetitive art of hachures. Before the advent of widespread, precise contour surveying, an older, more artistic method was used to convey steepness. Hachures. Hachures are a system of short, thin, parallel lines used to indicate slope. They do not give a precise numerical elevation, but they give a strong visual sense of the land's steepness and its form. Imagine the map engraver taking their fine cutting tool to the copper plate. They approach the side of a mountain. On a gentle slope, the engraver would etch short, fine hachure lines that are widely spaced and light in density. On a very steep cliff face, the lines are etched much thicker and densely packed together, creating an area of heavy, dark shading. The darker the area, the steeper the hill. Hachures were often drawn as if light was shining down from the northwest, which meant that the southeastern slopes would receive more shading, subtly enhancing the three-dimensional illusion. The drawing of hachures was an act of repetitive, focused endurance. It required the engraver to draw hundreds, perhaps thousands of tiny, near-identical parallel lines for every single hill on the map. The hand had to maintain an absolute, even pressure to ensure the lines were consistent, making this process one of the most physically monotonous forms of cartographic labor. The result, while beautiful, was an artistic approximation, lacking the hard, numerical certainty of the contour line. The comfort of color. Hypsometric tints. The final method for showing elevation is the most visually soothing. Hypsometric tints, also known as layer tinting or elevation coloring. This system relies on a quiet, standardized, and internationally agreed-upon color scheme. It is designed to allow the map reader to immediately understand the elevation of a region simply by observing its color. This system is based on a simple, predictable progression. 1. Lowest elevations, sea level and below, are always represented by shades of deep green. The color moves from a light, airy green for slightly above sea level to deep, saturated greens for the lowest lying plains. 2. Mid-elevations, hills and plateaus, are typically rendered in yellows and light tans or oranges. 3. The highest elevations, mountains and peaks, progressing through shades of brown, moving to deep reddish browns for the highest ridges, and often culminating in pure white for areas of permanent snow or ice. This fixed color key is profoundly calming in its consistency. A map produced in one country will use the same color sequence as a map produced in another, allowing for universal, predictable interpretation. The process of applying these colors in mass printing involved large presses that laid down continuous, flat washes of ink over the paper, carefully respecting the lines and boundaries established by the contour intervals. The result is a map that feels organized, soft, and predictable. A gentle gradient of color, guiding the eye from the peaceful green of the seashore up the slow rising gradient toward the quiet, white stillness of the mountain peaks. Allow the thought of this gentle, predictable change in color, from deep green to soft yellow to steady brown, to guide your mind to stillness. The geometry of the contour line, the shading of the hachure, the constant, comforting logic of the hypsometric tint, securing the third dimension in its silent, proper place.
We have established the Earth's curves and the invisible lines of the grid, but a map remains useless unless the language it speaks is universally understood. The entire purpose of organized cartography is to communicate complex reality through simple, agreed-upon marks. We now turn our attention to the final, essential element of all maps, the legend or the key. This is the small, quiet box of symbols that contains the entire language of the map. It is the dictionary of geography. Settle in and allow your mind to appreciate the deep, quiet comfort of absolute global agreement on a line, a dot, or a small, predictable stamp. The necessity of uniformity. When a map is created, the scale demands that real-world objects, a 50-foot bridge, a 100-mile highway, or a vast forest, be reduced to lines and icons that are only millimeters across. If every cartographer invented their own symbol for church or railway line, the map would become an unintelligible mess of conflicting meaning. The convention of the legend is the quiet understanding that certain symbols must remain uniform and consistent across all maps, regardless of the country or language in which they are printed. This uniformity removes all visual uncertainty. It ensures that a traveler in America, looking at a map of a remote area in Europe, can instantly understand the difference between a paved road and an unpaved trail, or the location of a dry well versus a perennial spring. This reliance on shared, unexciting symbols is profoundly calming. It means that the chaotic, infinite variety of the physical world has been successfully reduced to a finite set of repeatable, simple icons. Standardized lines, the language of movement. The clearest example of uniformity is found in the depiction of transportation lines. Roads and railways are represented by specialized lines that speak immediately to their function and capacity. Imagine the subtle variations in these lines, each communicating a different level of importance and access. Major highways or interstates, often represented by two thick parallel lines, sometimes with a shaded border, indicating high capacity and access control. Secondary roads, a single, moderately thick, solid line, demonstrating a paved surface but lower capacity. Unimproved trails or dirt roads, often represented by a simple, thin dashed line, indicating the lack of pavement and the potential for unreliable travel. Railways, almost universally represented by a line with small, perpendicular hash marks crossing it, visually mimicking the cross ties of the track. Each line requires the map reader to perform a small, predictable mental transaction. Dashed line equals unpaved, therefore I must anticipate a slower journey. This reliance on predictable visual cues turns the potentially frustrating uncertainty of travel into a calm, systematic planning exercise. Iconic shapes, the quiet dot and square. Beyond the lines, the map key standardizes the representation of point features, small, discrete objects that occupy a specific coordinate. Buildings and structures are often reduced to simple geometric shapes. A standard black square or rectangle is the universal symbol for an unclassified building. Points of interest. Specific, important locations receive quiet, distinct icons. A small cross or a simplified drawing of a steeple for a church. A miniature flag or star for a capital city. A thin horizontal line over a thick line for a bridge. The consistency of these icons allows the map to remain clean and uncluttered. A massive factory building in the real world is quietly reduced to a small, neat rectangle on the map. This abstraction removes the visual noise of reality, leaving only the essential, organized data. The cartographer's discipline here is absolute. They must resist the urge to draw the building realistically, instead relying on the agreed-upon symbol, the comforting knowledge that a single dot is all that is required to communicate a massive structure. The predictable consistency of hydrology. Even the movement of water is subjected to this unifying convention. Perennial, year-round streams, always represented by a continuous single blue line. Intermittent or seasonal streams, represented by a blue dashed line or a line of blue dots, indicating the presence of water only during certain predictable times of the year. Lakes and oceans filled with a uniform flat wash of light blue or cyan. This use of standardized blue for all water features creates a visual language that is instantly clear. The sight of a continuous blue line on a map offers a deep, quiet assurance of a reliable water source, codified by the universal symbol for wetness. The comfort of the key box. Finally, the legend itself is placed on the map, a small rectangular box containing every symbol and its corresponding meaning. The legend is the silent contract between the map maker and the map reader. It is the one place on the entire map that speaks directly to the reader, saying, "Here is the entire language you need." Everything else is simply a repetition of these facts. The act of consulting the legend is a moment of quiet, focused certainty. It is the final reassurance that the visual chaos of the map is in fact entirely ordered and decipherable. The discovery that the confusing array of dots and lines is merely a straightforward, repeatable system is deeply calming. The establishment of this uniformity, this shared, unexciting language of lines and symbols, is the triumph of global cooperation over individual artistic whim. It is a testament to the soothing power of fixed convention. Allow the thought of those small, perfect icons, the dashed line, the solid blue, the simple square, to settle your mind. The predictability of the map key, ensuring that every small mark has a large, certain meaning.
We have reached the final segment of our long, unhurried journey. We began with the shadow in the well and the chalk line in the sand. We have witnessed a slow, methodical struggle to reduce the vast, curved earth into a flat, measurable rectangle. Now, we come to the quiet culmination of all that effort, the digital coordinate. The absolute, certain answer to the question, "Where am I?" delivered in real time by the Global Positioning System, or GPS. This system represents the ultimate triumph of the grid. It is the perfect, unexciting solution to the longitude problem. A solution rooted entirely in the simple, predictable nature of numbers and the constant, unfailing speed of light. Allow the thought of these simple, precise numbers floating silently in the air to settle your mind into a final deep state of rest. The quiet infrastructure. The satellites. The core of the GPS system is entirely abstract and profoundly simple. It relies on a network of dozens of satellites orbiting the Earth high above the atmosphere. These satellites are not dramatic. They do not send messages or warnings. Their only function is to continuously, relentlessly, and silently transmit a single, simple signal containing two pieces of unexciting data. One, the time, the precise atomic time that the signal was sent. Two, the satellite's position, the precise coordinate of the satellite at the moment of transmission. This signal is continuous. It is fixed. It is the ultimate, perfect timekeeper and position keeper, the perfect clock the 17th century navigators could only dream of. The calculation,
the constant speed of light. Your GPS receiver, the quiet device in your pocket or dashboard, does not receive its position from the satellites. It receives only the time and location of the satellite. The calculation of your own position is performed entirely inside the receiver, using the simple, unyielding constant of the speed of light. The receiver determines the exact time difference between when the signal was sent by the satellite and when the signal was received by the device. Since the speed of light is a known fixed value, approximately 186,000 miles per second, or 300,000 kilometers per second, the receiver can instantly calculate the distance to that single satellite. This process is repeated simultaneously for 4 or more satellites. Imagine 4 vast intersecting spheres of known distance. The only point on Earth where all 4 of those spheres can intersect is your exact location. This is the simple, quiet magic of trilateration. There are no shadows, no complex lunar tables or rolling ships to contend with. Only the clean, constant math of distance equals speed multiplied by time. The comforting readout, the coordinate pair. The result of this constant, rapid, and repetitive calculation is the final, comforting answer, a single pair of numbers representing your location on the grid. The answer is delivered in the precise language of the graticule we explored earlier, latitude and longitude. For example, your device might quietly display latitude 34.0522 degrees north, longitude 118.2437 degrees west. This coordinate pair represents a final, absolute level of certainty. It tells you that based on the precise measurement of time, you are standing at the intersection of a specific invisible parallel circle, 34.0522 degrees north, and a specific invisible meridian, 118.2437 degrees west. The numbers are often displayed with 6 or 7 decimal places of precision. This level of detail, down to the finest fraction of a second, is immensely satisfactory. It assures you that every step you take results in a small, predictable, and measurable change in the numbers. The end of confusion, a universal language. The GPS coordinate is the ultimate global language. It is a language of pure numbers, entirely free of national bias, linguistic ambiguity, or cultural interpretation. If you gave the coordinates 40.6892 degrees north, 74.0445 degrees west to any cartographer, surveyor, sailor, or scholar on Earth, they would all point immediately and precisely to the base of the Statue of Liberty. This universal agreement, achieved through relentless technology, provides a deep, quiet sense of security. The world is no longer a mystery. Every single point on its vast curved surface is knowable, measurable, and reducible to a simple pair of fixed, predictable digits. The great struggle of the ancients, the search for longitude, the worry over magnetic variation, the difficulty of precise angle measurement has been quietly solved by the relentless, predictable pulse of a distant, silent signal. Allow the thought of these simple, fixed numbers, the absolute certainty of the digital coordinate, to quiet your mind. You are placed. You are fixed. The world is measured.